So now we're going to be talking about what are called Taylor series. And so this is where we actually start learning to extend the concept of power series beyond what can be built off of a geometric series. Uh, and we've actually done most of the work for this when we talked about Taylor polynomials. Uh, the idea we're going to do with the Taylor series is take the Taylor polynomials out to an infinite number of terms. So remember that the Taylor polynomial is used to approximate a function. The higher the degree, the further away we can go from the center and still get acceptable approximations, knowing that we still need to talk about how do I know how far to go and what is considered acceptable. So, but the idea of it is if the degree of the Taylor polynomial approached infinity, that should give us our best approximations. And so that resulting infinite series is called a Taylor series. One name that you're going to hear a lot is a Maclaurin series. That is a Taylor series when the center is at x equals 0. So sometimes they will say Taylor series with a center at x equals 0. Other times they will just say Maclaurin series and not tell you the center, because you should know when you hear Maclaurin series, automatically the center is x equals 0. So the idea of this is we go ahead and start building a Taylor polynomial, but we keep going out to an infinite number of terms. Typically on the AP calculus exam, they're going to ask for the first 3 or 4 non-zero terms plus a general term. And I will be honest, the general term is the one that's usually challenging to write. So let's go ahead and find the Taylor series for the function h of x is equal to e to the x centered at x equals 1. So I'm going to go ahead and, because I know I'm going to need several derivatives here, I'm going to go out to the third derivative to help me see patterns. I typically find it nice to have 4 terms to help me see a pattern, but a lot of people can do it with 3 terms. And I want to see the pattern to help me write the general term for my Taylor series. So h of x is e to the x. This is really nice because those e to the x is the derivative of itself. Then I know I'm going to be plugging in all of my centers. Well, those all end up being e to the first. And remember that the whole idea here is I'm going to be doing h of 1 over 0 factorial times x minus 1 to the 0 plus h prime of 1 over 1 factorial times x minus 1 to the first plus h double prime of 1 over 2 factorial times x minus 1 squared, and so on. So I'm going to be plugging in my values here. So that's going to give me e over 0 factorial, and then times x minus 1 to the 0. I am purposefully not doing a whole lot of simplifying here because unsimplified will be easier to see patterns. And plus e over 1 factorial times x minus 1 to the first plus e over 2 factorial times x minus 1 to the second. Going out to a third derivative here, e over 3 factorial times x minus 1 to the third. And I'm now feeling pretty confident I can see a pattern. I'm going to have an e over n factorial times x minus 1 to the n. And then that continues on. And here is an infinite Taylor series that should converge to e to the x when I am centered at x equals 1. So then if I wanted to find the Maclaurin series for k of x equals sine of x, automatically, Maclaurin series tells me the center is at x equals 0. And that's important for me because I need the center to write this. So I'll be doing k of 0 over 0 factorial times x minus 0 to the 0 plus k of 0, k prime of 0 over 1 factorial times x minus 0 to the first plus k double prime of 0 over 2 factorial times x minus 0 to the second, and so on. So I need to start finding the values I need. So I have k of x, k prime of x, k double prime of x, k triple prime of x. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And actually, that'll just circle back up to the top if I keep that going. So I'm going to be plugging in 0 to all of these. Well, the sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. So I can go ahead and start plugging these in. I am going to simplify the x minus 0 part as I do this. So I'm going to have 0 over 0 factorial times x to the 0 plus 1 over 1 factorial times x to the first plus 0 over 2 factorial times x to the second plus negative 1 over 3 factorial times x to the third. And actually, that's going to keep repeating here. I'm going to be writing out a lot more terms than usual just because of all these zeros. So what I'm noticing is all of my even degrees are 0. And I can actually toss out all of my even degrees, meaning my exponent has to always be an odd number. So now the question of how do I only have odd exponents? Well, the answer to this is that if I want an odd number, odd numbers are defined as being 2n plus 1. No matter what I plug into n, 2 times that makes it even, and adding it 1 makes it odd. So 2n plus 1 is always an odd number. And if you doubt that, just start plugging in different whole numbers for n. You'll always get an odd number. If I wanted an even number, I just do 2 times n, because 2 times any type of whole number will give me an even number. So I want odd numbers. So for my general term, I know I'm going to need x to the 2n plus 1. And then I notice that the factorial in the denominator is always the same as the exponent. So that's going to be 2n plus 1 factorial. But then I'm noticing that the 1, sometimes it's a positive 1, sometimes it's negative 1. It's alternating. And what this means is that I have a negative 1 raised to a power. If I'm saying n starts at 0, which would work greatly for my powers, if n is 0, I'll have x to the first, and I'll have 1 factorial of the denominator, and negative 1 to the 0 is positive 1. Hey, that works. And I can check that with my other exponents. But there is my general term, and now here is my Maclaurin series for sine of x. That is not an easy one, I will be honest with you. It takes time. However, it is one we see a lot. In fact, there are 3 Maclaurin series that, quite honestly, you should just memorize, because we see these Maclaurin series often enough, and we use them to build other Maclaurin series, as a later video will go into. So these are the 3 Maclaurin series you really need to memorize, because these are the 3 that you're going to just experience over and over and over again. E to the x, 1 plus x squared over 2 plus x cubed over 3 factorial. Technically, I could even say this is 2 factorial here. But the general term is x to the n over n factorial. We just went through the sine of x, which is negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, because those should be odd. Cosine alternates as well, so I have a negative 1 to the n. but cosine is even, so x to the 2n over 2n factorial. And the way I keep these straight is graphically sine is an odd function, meaning it is symmetric around the origin. So if that's my axes, whereas graphically cosine is an even function, meaning that it is symmetric over the y-axis. And that's how I keep track that sine, I need the odd exponent and odd factorial. Cosine, I need the even exponent, even factorial, and both of them alternate with that -1 to the n.